My talk is about information-theoretic perspectives on learning algorithms. This is joint work with Adrian, who is a PhD student in the math department, Ankit, who is a first-year PhD student in the CS department, and with Poli. Right, so let me start with a simple example of kind of learning. Say you're given a bunch of points in R2, and you want to fit a curve that kind of approximates this distribution of points. And let's say you're given the class of functions that are allowed to use it's some polynomials up to a certain degree, and you're trying to find the appropriate coefficients to fit a curve to these points. I'm going to call this problem the problem of going from a bunch of points to a curve that fits in those points as a forward problem, okay, going from points to the curve. So, and here are two examples of curves that one might fit. Okay, so there's one on the left, and there's one on the right. And intuitively, it looks to us that the one on the right is like an overfitted curve, okay, and the one on the left seems like a proper fit. And the one intuition with completely non-mathematical intuition is the one on the right. See, looks like it's an overfit because it's too wiggly. Like it's trying to go through all the points and it's just too wiggly. Okay, and if you want a more concrete kind of mathematical description of what it means to be too wiggly, you could say that it's not very stable in the sense that if you were to change your x coordinate a little bit, your y coordinate changes quite a bit, so it's not very stable compared to the left one, which seems more stable. Right, so that's one perspective that is kind of popular in this area about how to characterize overfitting as by using some different notions of stability, like how wiggly the curve is, or how much does the output change when you change the input just a little bit. Right. I'm going to present one more kind of perspective on overfitting, and that's the following. So let's look at what I'll call the reverse problem. The forward problem was given a bunch of points, you want to go to a curve, or you want to go to some kind of an estimator. And the reverse problem is the reverse. Suppose you're given the curve, so you know the algorithm, or you know what method has been used to generate the curve. But now all you see is a curve, and now you have to go back and guess what were the points that must have led to this curve. Now, if you're given the curve on the left, then this problem is not that easy. Like all you see is this curve, and you want to figure out where the points are. So you know that the points were somewhere around this curve, but you don't really know exactly where they were. You could get some distribution on where they would have been. But on the other hand, if you look at this curve, then it's kind of easy to know where the points were. You'd see that the only reason why the curve must have gone here is because it was trying to fit a point there. The only reason the curve must have gone here was it was trying to fit a point there. So it's trying to fit all these points, and that's why it became wiggly. But in the process, you can also solve this reverse problem easily in this overfitted kind of curve. Right. So that's the perspective that this backward problem of guessing points from the output of your algorithm or from the output of your estimator is easier if you have overfitted the data. Right? And the one-line intuition is why that this is because somehow the curve on the right contains more information about what the original data set was compared to the curve on the left. Right? So that's kind of the perspective that I want to emphasize on in this talk, that there is some way of thinking about overfitting in terms of the information content. Like how much information does the output have in terms of the input? If you characterize that information, then it is possible to give some idea of overfitting. So I'll go into specific details of what it means to overfit the data and those things later on. But this is just a brief summary. So I'm going to explore this connection between information theory and some overfitting, characterization of overfitting. And I'm going to describe a bunch of algorithms, a large class of algorithms, which are often used to in these learning problems. And then I'm going to show that these can be analyzed effectively using information theoretic ideas. I'll then go to a different kind of bound. So these, in point 2, the kinds of bounds that I'm going to be using are motivated by mutual information. But mutual information does not have, not everything is great with mutual information. So in particular, I'll point out what are some shortcomings of using such mutual information bounds. And I'll describe like there are ways to get other kinds of bounds as well. And these will be using what is called the Wasserstein distance from optimal transport theory. And I'll end with some speculations and some open problems. Right? Okay. Okay. So here's the first thing. How do you think of a learning algorithm as a channel? Okay. So you can think of what is a learning algorithm doing? It's taking as input a bunch of points. So let's call it the data set S, which let's say is generated from some data distribution mu, and there are n IID samples. Okay. So you start. So this should be a capital N. You start with n IID samples as input, and the output is some estimator W. Okay, so if you're thinking of a curve, then maybe think of the coefficients of the polynomial or something. So I'm going to think of this W as sitting in some R to the D space. Okay? So you have an input data set, and then you have an output W, and your algorithm or whatever optimization process you're running is the channel. So it is taking an input W and producing an output. It's taking an input S and is producing an output W by looking at that S. Now, this might seem weird, like why would I think of it as a channel? So a channel in information theory is something, it's often easiest to think of as an additive noise channel. Okay, so you send a random variable through this channel, which is like the air wave or something, and what you receive is a noisy version of what you sent. So if you sent in X, what you often get is X plus Z, where Z is some Gaussian noise. But channels can be more general, that they can, it's basically just a collection of conditional densities. So it's the probability of output given input. So if Y is the output, a channel is just Py given X. If you tell me what X is, a channel is going to tell me what is the distribution of Y. Okay. So we are thinking of an algorithm as a channel, which means that we are thinking of probability of W conditioned on S as being the algorithm, which seems a bit weird because often when we think of an algorithm or an optimization scheme, there's like a closed form solution. So if you have a linear regression kind of thing, then the W is the slope of the line is kind of given in closed form in terms of your data set S. So it seems a bit weird to think of it as a channel because there seems to be no randomness in the.
Noisy channel.
Yeah.
Sorry.
Just correct it, be corrected. That's Gaussian noise.
duplicating into that box? And maybe there's a like of the connection in there. No, I mean the one on. You can know on the technician's door. Are they up here? Or? Yeah, I think it's just because it's not office on the right. Okay, maybe I need to go down too far.
Oh, okay. Yeah. Okay, maybe the HDMI is just buggy. VJ seems to be working. Misaligned. It's better. All right. Okay. So we have we want to think of a learning algorithm as some kind of a channel. So you take an input S and you're producing an output Y, and the channel is a collection of distributions P of W given S. So given an S, what is the distribution on the output W? And I said this is a bit weird because often your W is a deterministic function of your input. So the channel would seem like it's just a degenerate delta sitting at the intended output W. But often these days we use some kind of a random procedure like stochastic gradient descent or something, where the output is not always deterministic because it depends on the way you process data, because data is kind of processed in a random order. Like you don't take the whole data set at one shot and then get the output. You break it up into chunks, and those chunks are often random. So the output that you get is some kind of a random output. So it's close to the actual output, but it doesn't have to be deterministic. Okay, so that's why it kind of helps to think of the algorithm as a channel. But this is again a bit different from information theory, because in standard information theory, like communication or something, the channel is kind of nature given by nature. It's just a collection of distributions which is given by nature, and our job is always to figure out how should we deal with this channel, how to design codes or something to that work best for this channel. But here the difference is you're actually designing the channel. Like our job as a algorithm designer is to just come up with a good channel that leads to a W. And I haven't described what good means. So what does it mean to design an algorithm? Well, so the goal of designing an algorithm is to minimize some kind of loss. So the loss function is a function which acts on W cross X. So W is the space of outputs, and X is the space of inputs, and gives some value in R. And the best thing to do would be to actually set as W this particular quantity W star, which minimizes the expected loss for over the input distribution view. Okay, so if we can calculate this W star, then that would be the right thing to do, because this is on average going to minimize the expected loss. Right? But we can't really do this minimization because we don't know what the data generating distribution mu is. All we know is we have a bunch of samples x1, x2, xn, and we have to do something with it. So we can't really solve this problem exactly, but we can try to something related. So instead of minimizing this expected kind of loss, we can minimize the empirical loss, which is the loss that you have on the data set x1, x2, xn. Okay. Now at this point, I think things get a bit different from regular models, I think, that are considered in statistics, because in statistics there is often an underlying true W star, and you have an algorithm or an estimate, and you want to kind of show that the output of the estimate is close to that actual W star in some sense. But here there is no model, like there is no model that is describing how the W is related to the S or something. So I'll show on the next slide what is what exactly is the thing that we are trying to optimize here. But just to clarify that there is no model here, and we want to. All right, so okay, so what I want to emphasize is, so this is the empirical law. So any optimization algorithm or learning algorithm that we have is going to try and minimize this empirical loss in some sense. So it is going to look at that S, and it's going to try and produce a good W that minimizes the empirical loss. Right? Okay, so I'm going to define what expected loss is. So this is what I had on the first page. So the expected loss for an algorithm is given by following. It is the loss that the output W experiences when you run it on some unseen data point X. So there are two components in this expectation. One is this X, which can be thought of as a point drawn from the test set roughly. Okay. So you have a set S, which was your training set, like the data set S. Looking at that set S, we generated a W by running some kind of an algorithm. And once we have that W, we test that W on a point X, which that W hasn't seen before. Okay, so that point X is drawn from the true distribution mu. But this W is drawn from by this process, that there was someone generated a data set S, and then you ran your algorithm PW given S, that gave you a W, and then you find this expected loss on W and X. Okay, so this is probably the most important slide, because this generalization error is kind of the quantity that I'm going to analyze in this talk, and this is a very strange quantity. It kind of takes a while to understand what it is. Okay, so here's an explanation. So this loss that I wrote, expected loss, can be broken down into two parts. So expected loss is expected loss minus expected empirical loss plus expected empirical loss, okay, which I want to think of it as, this is kind of the test error, the error that you had on an unseen point, minus the train error plus train error. So this train error just cancels out and you get the same thing. But the expected empirical loss I'm going to define, which is kind of the train error, is this particular loss. So it is the loss that you get on your dataset S. So your dataset S was generated at random. Then we generate a W after looking at the dataset S, and then there is going to be some loss ln of W comma S that this pair W and S are both going to have. And we are going to take the expectation over all possible joint distributions. So this joint distribution again has two components. It has P of S, which is the randomness that comes from your dataset, and PW given S, which is the randomness that comes from the algorithm. And this generalization error is defined as the gap between this test error and this train error, or the another way to write down. So this quantity I've written here is the same as this quantity here, because the expectation is just 1 over n times sum of all these losses, which is the same as this. Right? So here we have the expectation of some function with respect to the product distribution, and expectation of the same function with respect to the joint distribution. Right? Okay, so there are two reasons for considering this expected loss in these two parts. So what we really care about is just this loss. Like if we can make this small, then we are happy, because it makes sense, right? As long as the output W is is performing well on unseen data, on the test data, that's fine. We are happy. But then why are we splitting it up into test minus train plus train? The intuition is that any optimization algorithm that we are employing is only has only access to this part, the training error or the expected empirical loss. Okay, so an optimization algorithm only tries to minimize this term, but in the process of minimizing this term, it might blow up this term. Okay, so often it's easier to analyze these two terms separately. Like you have an algorithm, so you analyze the train error separately, show that the algorithm is good enough to make the training error small, and then you have a second part which says that the algorithm doesn't blow up this other term, and this other term I want to think of as a measure of overfitting. Okay, and why is that? So this term, it's the gap between test error and train error. So if this number is small, it means that whatever output W you have performs as well on the training set as it does on the test set. Okay, so if it happened that it performed really well on the training set and it performed really bad on the test set, then you would know that it must have overfit to a data set. But if it performs kind of equally well on both these sets, then one would say that you're not really overfitting to data. Again, there is one thing to keep in mind, that just because an algorithm has good generalization error doesn't mean it's a good algorithm, because because as I said, what we really care about is this expected loss term, and it has two components. So you want both these components small. Just making it generalize well is not enough, because generalization error is only saying that it performs equally well on the training set and as it does on the test set. But the reason for that could be it might be terrible on both those sets. Like it might have a huge loss on the training set and a huge loss on the test set, but both those huge numbers are the same, and that's why it is generalizing well. So you really need to care about both these terms. But the taking care of this term is a part of kind of the analysis of the algorithm. So I'm going to assume that someone has designed an algorithm that is kind of the goal of that algorithm is to make the training error small, and my job is to analyze how this term kind of blows up. Okay, and then give some kind of guidelines as to how long should you run your algorithm, or should you really run your algorithm until it reaches the actual minimum, or should you just stop somewhere? Any questions here?
Will P of S be an empirical distribution on the test set, or will it be some
Right.
distribution?
So P of S, S is the data set. So it's x1, x2, xn, and it's just a product distribution on the training set. So you can think of it as x1, x2, xn it's just the product distribution mu to the n. If you have a product distribution here, like PS cross PW, then the way to interpret it is you are evaluating the loss function on a data set that W hasn't seen. So that would be the test set. And if you have a joint distribution, then it means you're evaluating the loss function on the data set that was used to generate that W. So then that's a joint distribution.
For this very generic set, it is possible that your generalization error is negative, is it?
It could be, yeah. It could be possible that it's negative. So we'll look at like the absolute value of generalization error and try to make that small. Yeah. Okay. So like for instance, like a really terrible algorithm that's great at generalization, just pick a W that is independent of your S. Don't even look at your data set S, just pick a W, whichever favorite W you want, and just pick it. And the result of that is this joint distribution PW given S is now going to be a product distribution because it never even looked at your S. So the S and W are independent. Awesome. Okay. Right. So if S and W are chosen independently, then there is a product here and there is a product here and 0. But so this is an algorithm that is generalizing really well, but it doesn't make any sense to use this algorithm because you have to look at your data set to generate the curve or any output. You shouldn't just fix a curve or generate the curve completely at random. So that's kind of the cautionary message, that just looking at this generalization error is not a great idea. You have to actually look at both terms. But I'm going to look at generalization error because I'm going to assume that the algorithm has been designed to minimize training error. Okay. Alright, so here's so the tools that I'm going to use are information theoretic tools. So here's like a one slide crash course in information theory. The main quantity of interest is what we call IXY, mutual information. And what mutual information does is it provides a way to quantify how much information does a random variable x contain about some other random variable y. Okay, so you can also think of it as some notion of correlation, or a more a nuanced notion than just finding correlation between two random variables. And it's defined as follows: it's a scale divergence between the joint distribution and the product distribution. So if the two random variables were indeed independent, then you would have a KL divergence between a product distribution and a product distribution, which is 0. That makes sense. If two random variables are independent, you would want the information to be 0. And since it's KL divergence, it's always positive, so there's always some information between x and y. And it satisfies these two nice properties that I'm going to need. The first is what is called data processing property. So data processing means that if you have three random variables which are kind of like in a Markov chain, x to y to z, then information decays as you go downstream. So x contains, so this random variable y contains more information about x than z contains about x, because as you go downstream, you lose information about x. So that's data processing. And the second is the chain rule, which just says that if you want to calculate how much information does y contain about the pair x1 and x2, you can first find the information between y and x1, and then now that you know x1, then you find what is the additional information between y and x2, having found out x1. Okay, so these are the only two properties that I'm going to need about mutual information. All right, so here's the result that kind of started our work, which is from last year. So this paper said that there is a way to bound generalization error for an algorithm by this quantity, which is the mutual information between your data set S and your output W. So the assumption was that the loss function is somewhat nice, that it is sub-Gaussian for every W in your set, calligraphic W. And the thing to note here is that, again, if S and W were actually independent, which means you did not even look at your set S while generating W, then generalization error is 0, just as we saw before. But the more dependent S and W are, the worse this bound gets. And again, intuitively that makes sense, because the more dependent S and W are means that you're really relying on your data a lot more to kind of generate this curve. So it might be that you are overfitting. Okay? So that's the result, and I would call this a data dependent bound because the sub-Gaussianity depends on the data distribution X. Okay? And again, compared to notions of stability that are traditionally considered in this kind of learning literature, this is a bit different. So the kinds of notions of algorithmic stability that are often considered are the following: that you have an input, if you have an input data set and you have an output, and stability is defined as following: that you change your input a little bit by maybe modifying just one of your samples or just removing one sample, and then look at how much does the output change when you do all these kinds of perturbations of your data. And if the algorithm output does not change a lot after these perturbations, then you call the algorithm stable. And there have been a lot of work in this area about how, if your algorithm is stable, then it generalizes well. So this kind of notion of stability, or this mutual information based idea, is a bit different because there's no data perturbation going on. We just measure what is the mutual information, and then that seems to be a way to bound generalization error. And I just gave a one-side proof sketch, but the idea is generalization error in the earlier slide was a difference between two quantities. Some function which was function whose expectation was evaluated according to the joint distribution, minus some function whose expectation is evaluated according to the product distribution. And recall that KL divergence is essentially some measure of how far away the joint distribution is from the product distribution. So it's not mutual information, it's some notion of distance between joint and product. So it's not surprising that we can bound this quantity using mutual information. So that's how mutual information kind of shows up in this proof. Okay.
So was the F on the...
Sorry?
So F appears on the left-hand side but not the right-hand side, is that right?
Yes. So the way F shows up is F is assumed to be the sigma sub-Gaussian under the product distribution, so only the sigma part shows up on the right hand side. Yeah. So for all F which are same, of course, in the same barcodes. Okay. So what we wanted to do was to actually use it to algorithms that people actually use in these days. So for instance, if you were actually using an algorithm like stochastic gradient descent or something like that, we know what the algorithm is. We know how W is generated after looking at S. But how do you calculate mutual information, right? Mutual information is this really strange quantity. You need to know precisely what the output distribution is for a particular input distribution, and then we want to be able to bound it. So that was kind of a question. Like this seems like a great idea. If we can just calculate mutual information, then we'll be able to use all these bounds, right? And the insight that we had was you don't really have to look at the final output W and then figure out how to bound it, because most algorithms are kind of iterative. So you start at some W and you generate a W1 by maybe looking at a part of a data set. Then you look at, so the picture I have in mind is basically stochastic gradient descent. You start from a W, you figure out a direction of gradient that you want to go in, or just regular gradient descent, that's easier to think of. So start from a W, you take a direction of gradient, move in that direction by a certain step size, and then take the new gradient there, move in that direction, take a move gradient there, and ultimately you settle down at some point that seems nice. Okay. Right, so this is kind of the rough idea that we generate these set of iterates, W0, W and WT, and the final output that we give is either the last point that we ended up at, or it's some function of these iterates, like often even something like the average of the iterates is used. But anyway, it's something that depends on the iterates. So if we were able to bound the mutual information between this final thing and what you started out with, by just controlling how much information is lost or gained at every iteration, then we can kind of add up this mutual information over iterations and then get a bound on the total mutual information. So that's like the very high level idea. You want to get a bound on IWS. W is the final thing. The final thing is obtained by taking small steps. So let's just bound what happens in one step and then get a bound on the whole thing. Right. So this is the class of algorithms that we ended up looking at. The class of algorithms is, again, as I said, these iterative algorithms. So you're sitting at the current estimate, so that estimate at time t-1, which I call wt-1. Then you sample a point zt. So that sampled point can be like a completely new point, or it might be something that you resample from your data set S. So you sample a point, you compute a direction to move in. So you decide I'm going to move in. So for instance, you might calculate the gradient of the loss function for that point ct, and you move in that direction by a certain step size eta t. And then we do something odd, which is that we move in that direction and then we deliberately add noise, which means that you move in the direction and then you just take a random step in some completely arbitrary direction. And the reason for that is twofold. One is that we want to be able to escape local. So if we were just following the gradient, for instance, then we might get stuck in a local minimum. And if you deliberately add noise, you check, and you might hopefully jump out of the local minimum and then go and explore other regions of the data set. And the second reason why we are going to be adding noise is we want to control information, and adding noise is kind of the nicest way, like to make sure that information decreases. Okay, so that's our final update equation that we start from. So for every wt-1, you get a new point, find the gradient, move in that direction, and then add some noise, and then you get a new point wt. And that's how you generate all your w's until some fixed time capital T, which is maybe the budget of how long you want to wait, and then you output the final w, which is some function of your iterates. Right.
And the different components of w could be quite different things. Presumably, they're model parameters, are they? Is that?
Yes.
So,
yeah. I'm just thinking of it as a set in RD. So, for instance, like the coefficients of the polynomial that I'm fitting. So.
Yeah, I guess in that case they would have different dimensions, right? So then I would, maybe it's just a detail, but I guess you would have to normalize it.
I see. Yeah. So maybe like the polynomials have some fixed highest possible degree, and then yeah. Alright. So there are three assumptions that we have. Basically, one is the basic, say you want to use these mutual information kind of bounds. We need this one assumption about subgaussianity of the loss function. The second assumption is about the specific algorithm that we're using, that if you're sitting at a point and for some instance the gradient or direction calculation turns out to be huge, you still don't take a huge step, you always take bounded steps. And the last assumption is kind of critical, which is saying that you don't look at how your algorithm has progressed so far to decide which point to sample next. Right? So if you are keeping an eye on the W iterates, and you are allowed to look at the W iterates to sample, then you could kind of you could influence the algorithm or the gradient step to move in certain directions that you want it to move in, because you could just pick points looking at those W's. But you're not allowed to do that. Okay, so the points that you generate, your data set S and the resamplings of the data set S, are this procedure has to be done without looking at the W algorithm, or without looking at how the iterates have been progressing. And the way to think of this as a graphical model is you first say sample this data set S, which is IID x1, x2, xn. And once you have this data set S, you can resample it however many times to generate these ZIs. So Z1 could be, so Z1, Z2, Z1, Z2 ZT can be any procedure that you might have used to get samples from S. So you could just cycle through the data a bunch of times. Those could be, or you could pick randomly from S and then generate your Z1, Z2, ZT. It can be anything. As long as you don't look at the W's while generating Z's, you can do anything. And then the W sequence is by using this update. So there is some kind of a Markov property that goes inside, and you get this nice structure of a graphical model. Okay. All right. So our main result is the following: that if you want to control the mutual information between the input and the output in this process, there's a way to bound it using this formula. So eta t is kind of the step size, and sigma t square was the amount of noise that we added at each step. So given an algorithm, we know what eta t and sigma t are going to be, so we just plug in here and find out what this bound is going to be. And so I guess two things to mention here. One is that this bound is in the form of a sum, and that is because we are bounding information at each step, and then we are summing up all these informations, and that's why you're getting a sum there. And the second thing is this bound is depending on t, where t is the length of time you ran the algorithm. And this also is intuitive, because it's saying that if you run, the longer you run the algorithm, the better you're optimizing empirical loss, so the larger the chance that you're going to end up overfitting. Okay, so this is kind of related to some work on early stopping. So it is saying that don't run your algorithm for a very long time, just stop it early, because stopping it early will make sure that you don't overfit. All right. So here are some implications. So I'll just say what they are. I said that there is a way to bound generalization error using mutual information. What I showed on the previous slide is a bound on mutual information. Now I'm not going to do anything but just take the previous results about bounding generalization error using mutual information, plug in our bound of mutual information, and get these results. So this gives this one particular bound, which is kind of bounding the expected error, and there is also a high probability bound that we can give in the same way. But again, these are just kind of plug the mutual information bound in existing results, and out pops these two results. So I'll not spend too much time on these. And all right, so here's an application. So there is one particular learning algorithm called SGLD, which stands for Stochastic Gradient Langevin Dynamics. And what it means is precisely what we are doing. So what stochastic gradient Langevin dynamics means is that suppose you're trying to minimize a function, and you're using regular gradient descent. You take a step in the direction of the gradient, and then you get this gradient going to the minimum of the function. Stochastic gradient descent, Langevin descent does the following. You take a step in the direction of the gradient and deliberately add noise, and you keep doing that. So this is precisely what we are also doing. So you take a step in the direction of the actual gradient and keep adding noise. And again, the reason for that is it is often helpful in escaping local minima, and also helps you to in kind of Monte Carlo simulations. If you want to generate a specific distribution of W, then you want to add certain kinds of noise to the step that you take. So this turns out to be useful in sampling as well as in optimization. And so what we said is this seems exactly like what the class of algorithms that we are looking at. So we can just plug in what do people usually do in stochastic gradient Langevin dynamics. They apparently choose the noise variance to be comparable to the step size eta, and they run the algorithm for a certain number of epochs. So if you just plug in what the standard kind of components there are, you get this particular bound which says that if you're using SGLD to minimize your function or to as a learning algorithm, then you have a guarantee that generalization error will be bounded by something like something over square root n. So this is not really the sharpest possible bound one could have. We know of one result from last year which says that we can get a bound of 1 over n, but since our bounds are kind of using mutual information, they are more general. Like we don't really need to know the specifics of the algorithm, like how are you generating the final W looking at your iterates. None of these things really matter as long as it's some function we are trying. Okay, so that's kind of the advantage of using something as general as mutual information.
Well, in the original expression you have for the mutual information, when sigma is absent or sigma goes to 0, the thing blows up on the previous slide, I guess, on the previous.
Yes, but there is also an eta.
Yeah.
So what SG, so it kind of depends on how your step size and your noise are behaving with each other. So in SGLD, sigma square is chosen to be equal to eta. So this sigma square cancels out with one of the etas there, and the etas are chosen to be like 1 over t or something, 1 over I. So if you were summing up from 1 to t, then the sum of the etas would be something like log of t. So that's why the log term is showing up there, and the sigma is kind of cancelling out.
But I guess I just was wondering why, even if sigma was 0, would you not expect the mutual information to increase gradually, whereas here it looks like it diverges? But
right. So the problem with sigma equal to 0 is, I'll go into it in a little bit, but the reason is we really need sigma to, okay, so if sigma is equal to 0, the right hand side actually blows up to infinity. And the reason for that is mutual information is actually becoming infinity. Even though the algorithm might be good, so the algorithm might not be any different from adding very little noise to adding zero noise, but unfortunately adding zero noise blows up our bound. So even though the algorithm might be good, the bound is bad. And I'll skip this, but there are also some other kind of related algorithms which are not exactly like SGLD, but they try to make, so SGLD is an extremely noisy algorithm. The amount of noise you add after a gradient step is pretty big, but you can reduce the amount of noise by by using a different kind of a noise distribution. Instead of a Gaussian noise, you kind of add uniform noise in a ball, but you also scale the variance of that noise, and you get a different kind of an algorithm. And these algorithms were proposed, I think, in the past 2 or 3 years with the goal of escaping local minima. So because you add less amount of noise, I think these algorithms are provably escape a certain basin of local minima, but after that they make those stuff. Okay, and we can bound mutual information in all these kinds of algorithms, and once you bound mutual information, then all these other generalization error bounds also follow. Okay, just one slide to say that this also extends to more complicated looking algorithms like these. There are certain kinds of algorithms which are momentum based optimization algorithms, and what they do is you're also allowed to use kind of past information of the previous gradients to decide where should you take the next step. Okay, so somehow this term WT is keeping track of the previous gradients, and the step that we move in the future depends not just on the current point and not just on the kind of current gradient, but also somehow on some memory of the past gradient, and then you kind of move. And I just wanted to say that you can also use these bounds for these general algorithms, but the only difference is you now treat this v, which is called the velocity vector, and the w as one single output, and then bound mutual information in that. Alright, so here's a proof sketch, and the proof sketch is like, as I showed in the picture, that when you draw the graphical model, there's a very nice clean description of the graphical model, and that means that there are a lot of Markov chains in this in these random variables that we can exploit. And the first Markov chain is this one, that you have a data set S. After looking at the data set S, we created these resampled versions which were Z, and from Z we created the iterates W0 to T, and from the W we created the final W. So this is a nice Markov chain. What we wanted to bound was this mutual information I, S and W, but data processing says that I, S, W has to be upper bounded by this information between Z1, T and W0, okay, because they are closer and I, S, W are further apart. And to bound the mutual information between these two guys in the middle, you can use basically the chain rule of mutual information and show that this mutual information is exactly equal to the sum of all these stepwise mutual informations. Okay. So in general, if you want to expand this, I mean, you can always expand I, Z1, Ti, W0 into some kind of an expansion, but it doesn't always look this neat, and the reason why it looks this neat is because of another Markov chain that is kind of hiding in the structure. So this makes sense. So what this is saying is that the total mutual information between all your iterates and all your data points Z is bounded by the mutual information between Wt and Zt. So this is saying you're sitting at Wt minus 1. So conditioned on Wt minus 1, how much information does the next point, Wt, contain about the point that you used to reach that next point? So you're sitting at Wt minus 1 and you sampled Zt, and then you looked at Zt and moved to Wt. So how much information is there between Zt and Wt, knowing that you were sitting at Wt minus 1? And if that mutual information is small, then this overall sum can be made small. Okay. Okay, this is going a bit more, bit deeper into information theory, but basically it's saying that mutual information has this another expansion which uses the entropy function, and because we are using these nice distributions like Gaussian distributions, we know majority of these things in closed form, so we just kind of just plug in the expression of entropy of a Gaussian into this expression and then get the bounds that we want. So you can probably not pay too much attention to this round. Okay, so here's the slide about why mutual information may not always be the right thing to use to get bounds on this kind of generalization error. And so mutual information is great. It is kind of the unique measure of, a unique correct measure of information between between variables x and y. But then it suffers from all these other problems that are basically stem from the fact that there is a KL divergence in the definition. And it says that sometimes mutual information is just infinity. Right? And for instance, this happens when if you want to find information between x and some function of x, say x square. So mutual information between x and x square turns out to be infinity. And that's not good, like, because all our bounds are like, we are upper bounding something using mutual information. And if that becomes infinity, then the upper bound is just useless.
In what sense do you mean it's unique, correct?
So it is the unique correct measure in the sense that there are a bunch of axioms that one would want any reasonable notion of random, any reasonable measure of randomness or things to satisfy. Like if you take two independent things, then the total randomness should be the sum of the randomness in each of them. So there are some natural axioms that you can start out with, and that gives rise to a functional equation, and the unique solution turns out to be mutual information. Yeah, and one consequence of this mutual information shooting to infinity is that you can't use it for standard algorithms like stochastic gradient descent, because they don't have somehow in STD you don't have this noise component, and because you don't have a noise component, when you try to do these calculations for mutual information, they just shoot up to infinity. So that's kind of one bad aspect of using mutual information, and that's why I said that this noise part is in fact essential to use mutual. If you don't have noise, then the bound is just useless. So we need noise to make the bound useful, right? And so I'm just going to suggest some ways of getting past this block of how to not. What else can we use if we don't want to use mutual information? And the suggested idea is something like a Wasserstein distance. So I'll just explain what that is. So I'm from Wisconsin, and I've just got a house, and it snowed a lot this winter. So you have to shovel snow, right? You have to shovel snow from your driveway to the neighbor's driveway, say. Okay, and you have a pile of snow here, and you want to move this pile of snow there, and you want to figure out how much effort does it take to move this pile to that pile. So Wasserstein distance is essentially a way to calculate how much effort it takes. Okay, so it's a way to say that if you want to move this pile to this pile, then it gives you a transport plan. It says move all the snow here to that region and kind of spread it out in this way. And there is some cost associated to carrying each unit of snow from here to there, and you just integrate over this cost. Okay, so mathematically, if you were to write it down, if the cost is something like the distance squared or distance to the p, then it turns out that if mu is the original distribution of snow and nu is the new distribution of snow, then the total effort that you're going to be putting into moving this from there is some this expected value, where you're minimizing the expected value over all possible joint distributions that have the correct marginals mu and nu. So this joint distribution is kind of the transport plan of how you should move mu to nu, right? And just then, Wasserstein distance have turned out to be extremely useful. In particular, just want to point out that W1 and W2 are more kind of used in theory than the other distances, and there is a lot of fascinating theory in particular for W2, which can be found in this book by Cedric Villani, which is. So there are lots of deep connections of optimal transport theory to information theory, as well as analysis and partial differential equations and stuff.
That's W1 is what you have in the formula there, or the second formula.
Oh, the second formula? No, it's W2. So the optimal coupling in W2 for is so just in R you can get a nice closed form.
Yeah, you generate a uniform and you do have -1 of u.
Yes. Oh yes. Yeah, that should be a square. Yeah. 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 Okay. So just maybe show this theorem and maybe jump to speculations after that. So the reason why we looked at Wasserstein was, one, we wanted to do away with this sub-Gaussian assumption, because we can't really check if the loss function is sub-Gaussian in your input distribution if you don't even know what your input data distribution is going to be. So we relaxed that and said, let's just assume that this loss function that we are going to use is Lipschitz. So now it doesn't depend on the input distribution, but what does depend on the input distribution is this the bound on generalization error that we end up getting. That we get this bound that if you were to make this Lipschitz assumption, then you get this very odd looking bound on the right hand side. And at first it looks really weird, like it's not clear what it is saying, but I find it easy to think of it as some kind of variance measure in the space of distribution. So for instance, PS is your distribution on the data set. PS given W is is the posterior distribution. So once you know W, what is the distribution on S given W? And this is trying to measure like the distance between PS and PS given W. So if this were like a squared norm, this is kind of like the variance, I guess. Like you try to measure the distance between ES, PS, QW, you square it and take the square root of all that. So it's some notion of how spread out is the set of PS given W's with respect to PS. Okay. So that's just for interpretation. I don't really have a very nice way to think of this bound so far. It just it's just some bound that is guaranteed to not blow up to infinity at least, because it's not mutual information based bound. Right. So in general, you can't really compare the mutual information based bounds with this Wasserstein bound, but in some special cases you can compare. And in particular, there are these kinds of transportation inequalities, which try to bound KL divergence, which try to bound Wasserstein distance in terms of KL divergence. And if your input distribution satisfies a transportation inequality, then you can show that there is a way to get a bound on that strange quantity I showed on the previous slide in terms of mutual information. And in particular, we could show that this was precisely the bound of the Wasserstein bound that we had. We could show that this is smaller than the mutual information based bounds, which is nice, because not only so this bound can also blow up to infinity, but this won't blow up to infinity, and it's also better than that bound even when it is not blowing up to infinity. So that's nice. The same kind of result holds for a different kind of transportation inequality as well, but that's not super important. Okay, so I'll just stop at the speculations now. So what I said was, like, there are two ways to think about this idea of overfitting. One was the idea of stability, which is saying, like, how much does your output change when you perturb your input a little bit. And the second was this idea of information, how much can you guess about the input when you know your output. Right, so I like to think of them as something like a property of the forward channel and the reverse channel. Stability is a property of this forward channel. How do you generate a W looking at S? It seems like the way to bound generalization is to look at this backward channel. Like, if you know W, how much of S can you guess by looking at that W? Again, I don't really have any concrete kind of relations between these two things, but it just seems like an interesting way to think about this problem. And this is some more connections to information theory, which I can probably skip. And there are a bunch of open problems that I'll end with. So in particular, I'll focus on this, that the notion of Wasserstein-based mutual information replacement that we have turns out to be, instead of the KL distance between the joint and the product, we have the Wasserstein distance between the joint and the product. And this is a very nice measure. It's not blowing up to infinity, but I don't know if it satisfies anything like chain rule or data processing inequality. And if it does, then we can do something else with it. But so far, at least, I don't know what are any nice properties that it satisfies. So that might be something to think about. Okay, so I'll just stop here. Thank you.
So I just trying to think about the sort of how general this is in terms of how you sort of randomness you can inject in through your algorithm. Let's say you're doing knockoffs, using knockoffs of variable selection, right? You generate a knockoffs of random.
Right.
Would that fall within your framework?
I have to check, but I feel like most, as long as I can write down the mutual information expression, I can analyze it. So the only reason why I think we are using Gaussian noise is because it leads to these very nice clean bounds. So that's the technique that we're using to add Gaussian noise to make our input noisy. But I imagine that you could use different techniques. Like, for instance, the idea of knockoff is to just change S to some new S tilde, which had some fake points added with the actual true data set. So the point where you land up, so you're essentially making the gradient calculation a little bit noisy. So instead of looking at the actual gradient, you're looking at some noisy version of the gradient. You can characterize the amount of noise that is there in the gradient step, then that will lead to some